Welcome. In today's video we're going to look at a few examples for the computation of integrals over boxes using parameter integrals. So as the first example, we'll return to one that we've seen already. We're using the function f of x1, x2 is 2 minus x1 minus x2. And we'll integrate that over the box b 0, 1 squared. So we'll just go from 0 to 1 in both directions. Okay, to integrate that, we'll use the method of successive integration. So this integral f of x dx over b. By Fubini's theorem, this can be evaluated by successive parameter integrals in any order. The function f is continuous over the box. So we can, for example, choose to integrate with respect to x1 first, and then integrate the result with respect to x2. So the outer integral will be with respect to x2. And again, you can see I'll usually denote the variable of integration with the integral bounds as well. That makes it easier to spot which integral we have to evaluate. Okay, and the inner integral will be with respect to x1. The boundaries are the same, doesn't make a difference. F of x1, x2, dx1, dx2. Okay, so this is the integral we want to evaluate. First, let's substitute the actual function in there. That's 2 minus x1 minus x2, dx1, dx2. Then we'll do the integration step for the inner integral first. So we integrate that function with respect to x1. Now that is 2x1 minus x1 squared over 2 minus x1, x2. Evaluate it from 0 to 1. And we'll have to integrate the result once more with respect to x2. So what we get here is, let's evaluate the inner expression. This is 2 minus 1 over 2, so that's 3 over 2, minus x2. Integrating that with respect to x2 yields 3 over 2 x2 minus x2 squared over 2 for x2 from 0 to 1. And then we substitute the boundaries, and that gives us 3 over 2 minus 1 over 2 minus 0. So the result here is 1. Okay, so that is the integral of that function over the box 0, 1 squared. You can try the other order at home. You'll find there's not much of a difference here. You already know the parameter integral with respect to x2, so just integrate that once again with respect to x1, and you should get the same result of 1 regardless of which order you choose. Now let's try something else. Let's try something a little more complicated. So that's our next example here. We want to integrate a function from 0 to 1 in x1, and then let's make x2 different from 0 to pi over 2 in x2. And the function term is x1 times cosine of x1, x2, dx2, dx1. Okay, I've chosen x2 for the inner integral, more or less arbitrary. We'll try the other direction in just a minute, but let's first see how far we can get with this order here. Okay. So for the inner integration, what we can see, and actually the reason why I chose that is the x2 variable only appears once here in the cosine function. So this can be regarded as a simple constant for the integration with respect to x2. So what happens if we integrate that with respect to x2 is we get this x1 constant, and then we need to integrate the cosine. The integral of the cosine should be a sine expression. So we get something like sine x1, x2. If we differentiate that, then we get cosine x1, x2. And then we have to multiply with the differential of the inner function here. That differential would be x1. So for the integration, we need to divide by that factor x1 to get the correct result. Okay? So this is the integral. And we want x2 from 0 to pi over 2 dx1. Now, if we substitute those bounds here, what we get in the integral expression here, first, you'll notice that x1 and 1 over x1, that just cancels out. So we're just left with that sine expression. The sine of pi over 2 times x1. That's the upper bound. Like this. And then we subtract the sine at x2 equals 0. So that's the sine of 0, which is just 0. Okay, so we need to integrate that with respect to x1. And again, we need to integrate a sine expression. The integral of the sine is the negative cosine. So that's going to be an expression with a negative cosine in there. x1 pi over 2. And again, if we differentiate this expression, we get back the sine of x1 times pi over 2. And we need to multiply with the differential of the inner function, and that will be pi over 2. So for the integral, we need to divide out that factor, and that means we need to divide by pi over 2 or multiply by 2 over pi for the correct integral. Okay, so this is, again, boundaries for x1 from 0 to 1. And now we can just evaluate that. For the upper bound, we get minus 2 over pi cosine of pi over 2. For the lower bound, we get plus 2 over pi cosine of 0. The cosine of pi over 2 is 0. The cosine of 0 is 1. So we're left with just 2 over pi. That's the final result for this integral here. Now, Frobenius theorem says it doesn't matter which order we choose here. The result will always be the same. So let's try this and exchange the order here. Let's try to first integrate with respect to x1 and then with respect to x2, see what happens. Right, so we just change this order. The expression we integrated was x1 cosine of x1 x2 dx1 dx2. Now the inner expression now contains this x1 here and this x1 here. So we have two x1 expressions. That makes things a little more complicated. What we are going to do here is we're going to use partial integration. We're going to say that, well, this is u This is v prime. And then by partial integration, we will get rid of that x1 factor because we'll differentiate that out. Okay, so that's the first step. We leave this x2 integral on the outside. And we'll do partial integration on the inside. Now, first step is we get u times v, so this is x1 times, and now the integral of that cosine expression, we know that already. The integral of that cosine expression is the sine of x1, x2. We integrate with respect to x1, so we have to divide that by x2 to get the right value. Okay, so that's for x1 from 0 to 1. Minus, and we're going to subtract another integral here from 0 to 1 again. And then we need to integrate v prime and differentiate u. So differentiating u is just a 1. And integrating v prime, we just did that. That is the sine of x1, x2 divided by x2 dx1 and all that dx2. Okay, let's see. So this outer integral here, that just stays here. Let's evaluate the inner integral. So what do we have here? For x1 equals 1, we get the sine of x2 times 1 over x2 minus, and for x1 equals 0, we just get 0. Then minus. Now this other integral here, now we are left with just one x1 variable, so that's not that much of a problem. So we have 1 over x2, and then we integrate that, and again that's the cosine of x1, x2. We did that already, over x2 for x1 from 0 to 1. And all that needs to be integrated with respect to x2. So evaluating the inner terms, what we get is here, that's the sine of x2 over x2 minus, let's see what we get here. 1 over x2 squared, we can just take that out. And then we are left with the cosine of x2 minus the cosine of 0. The cosine of 0 is 1. Okay, so the integral that we have to solve now with respect to x2 is sine of x2 over x2 minus cosine of x2 over x2 squared plus 1 over x2 squared dx2. Now that looks hard to solve, to say the least. I mean, this part here, that should be feasible. But what about this part here? So sine of x2 over x2, cosine of x2 over x2 squared. So I have no immediate idea of how to solve that. And I'm unwilling to dig deeper here. So the message that you should take from that is, theoretically, the order doesn't matter. Both orders will yield the same result. But in practice, the order can make a huge difference. And what we saw here is in the first attempt with this order, integrating with respect to x2 first and then with respect to x1, we arrived at the result 2 over pi this here pretty seamlessly. Not much of a problem here. When we tried the other order, we arrived at an integral that we are seemingly unable to solve. Okay, so we know what the end result would be, actually. Of course, that would be the same result as with the different order that we tried before. But we don't know how to actually compute this particular integral here. So while the order of integration does not matter in theory, it can have a significant influence on the difficulty of computation. And that's the take-home message from this example here. Okay. While the order of integration does not make a difference for the result, it can significantly influence the difficulty of computation. So if you find you're stuck with an integral that you can't solve, then maybe you go back a step and try a different order of integration, and that might actually help. So that's the message that you should take from this particular example here. Okay, that's it for the examples for today. There will be more examples on the exercise sheet, of course.